Here we're going to talk about structural isomers and hard-soft acid-base theory when it comes to coordination chemistry. So isomers are compounds which have the same chemical formula but have different structures. You're familiar with isomers already, especially in terms of organic molecules. We're going to talk about two different types of isomers, again, similar to organic chemistry. We have structural isomers, so you have different atoms that will be bonded to the metal center, so the connectivity is actually different. These are also called constitutional isomers. You may be familiar with that term as well. And then you have stereoisomers. So from organic chemistry, this was R&S configuration and that sort of thing. You also had stereoisomerism in terms of cis and trans with an alkene, let's say. We've already kind of introduced some of that in terms of coordination compounds having different stereoisomers, like a cis and a trans situation, or FAC and MER, which we'll talk about later here. But for this one, we're going to focus on the structural isomers first and foremost. So here's kind of a flow chart for determining the type of isomer that you're dealing with. So first of all, they have to have identical formulas for them to be isomers at all. And then are the bonds between the same atoms? So is the connectivity the same? If the answer is no, then you're in a structural or constitutional isomer. And there's going to be four of them that we're going to talk about here: ionization isomers, linkage isomers, coordination isomers, and hydrate isomers. These are all structural isomers. If the answer is yes, meaning the connectivity is the same, there's a couple different things. There's stereo. These are stereoisomers, sometimes called configurational isomers, but generally we would just call them stereoisomers. And similar to organic chemistry, you're going to have kind of a diastereomer versus an enantiomer setup, where you have chiral non-superimposable mirror images, which is an enantiomer, which can also be called an optical isomer, and then diastereomers or geometric isomers. And there can still be different conformations, similar again to organic molecules, where you have slightly different bending or twisting of these individual bonds and that sort of thing as kind of a subset. So again, here are the four structural isomers that we're going to briefly talk about: hydrate isomers, ionization isomers, coordination isomers, and linkage isomers. So a hydrate isomer, it's not very common, but it was utilized in Werner's development of this structural coordination chemistry. So this is a good example where you can have three distinct crystalline compounds, and one was violet, one was blue-green, and one was dark green. And you can see that the only difference here is actually whether the water is a ligand or if the water is just hydration in the crystalline lattice. So similar to hydrates that are ionic compound hydrates, here you can have kind of a different sort of hydrate setup where the hydration in the crystalline structure, here you have 0, 1, or 2, but the difference being the amount of waters that are actually inner sphere coordinated as a ligand to the metal center. And again, all three of these have the same chemical formula, which is important. And this is actually a specific subset of ionization isomers. So ionization isomers have the same chemical formula, but they produce different ions when they're dissolved in a solution. So the same sort of setup here, where you have different atoms or ligands that are either inner sphere coordinated or the counter ion. So you can see where you have, let's say, bromine, in this case as a counter ion, in this first case as a counter ion. But in the second case, it's actually inner sphere coordinated. It's actually formally a ligand where it has replaced the chlorine and the water. So ionization isomers are with any ligand, kind of switching them between formally as a ligand or a counter ion, where the hydrate isomer was specifically with water. So that hydrate isomerism is a specific subset of these ionization isomers. You can see this is true for all of them, and they do have to have the same chemical formula yet again. Yeah. So the difference is which ion is present as a ligand and which ion is present merely to balance the charge, meaning a counter ion. So just by exchanging those, you get ionization isomerism. Coordination isomers involve the interchange of ligands among two coordination spheres. So here you'd have to have two coordination spheres. So two complex ions, for example, in which you are switching which ligand is connected to which metal center. So in that first situation, you have cobalt and chromium. You have those two complex ions. And you can actually then switch whether the amine or the cyano are connected to the cobalt or the chromium. So if you switch which ones they're connected to, then you get coordination isomerism, even though, again, the total chemical formula for these two complex ions end up being the same. So you can see that switching between the two different metal centers. And that's true also for if the two metal centers are of the same identity, but different oxidation states, like the second situation. And again, the total ratio of ligands to metals remains the same, but the ligands attached to a specific metal ion needs to change for it to be a coordination isomer. You also have linkage isomers. Some ligands have more than one possible donor atom, so you can either link them with one of those atoms or the other atom, for example, to that metal center. So there's two common examples here of ligands that form linkage isomers. So you have thiocyanate, which can coordinate through the sulfur or the nitrogen atom. And you also have a nitro group or nitrido, depending on if it's N coordinated or O coordinated to the metal center. So in the bottom, you have this nitro or nitrido group, depending on, again, nitrogen or oxygen, where you're coordinating to the metal center through the nitrogen in one situation, and you can see that that is actually yellow, so it has different properties. And you can interchange between them using light, where you can also have it oxygen coordinated. So these are linkage isomers, and it requires a specific type of ligand to be able to do that. Not every ligand can engage in linkage isomerism. And these complexes do have different properties like colors, depending on which atom is the donor atom. Here's some different ligands. So where you can have thiocyanado, which is S-thiocyanado, or isothiocyanado, which is N-thiocyanado, whether you're N linked through the nitrogen or linked through the sulfur. Like I said, there's also with the nitro versus nitrido would be N versus O linked. And then there are a number of factors that contribute to which atom behaves as the donor atom. And there's actually is some ability for us to predict that. Of course, at the end of the day, getting structural information is probably the best way to determine linkage isomerism. But I'm sure you could potentially think of some spectroscopy that could help us with that. But getting single crystal X-ray diffraction data would be probably the best way to confirm what linkage isomer you're dealing with. But there is some ways to take an educated guess, and that's hard-soft acid-base theory. That can help us with these predictions. And there are tables that can help with hard-soft acid-base, but there are some general principles as well that are worth knowing just as a starting point for trying to predict these things. So hard-soft acid-base theory, it's proposed by Pearson to explain the selective combination behaviors in inorganic chemistry. So for example, aluminum, when you find it in nature, it's found as an oxide ore, where lead and mercury are found as sulfides. So there are reasons for this, and it can be predicted with hard-soft acid-base theory. So if you're looking at a coordination compound in in a Lewis sense, the base can be classified by its size, charge, and polarizability, and you can categorize them into hard or soft, or somewhere in between, which is called borderline categories. Here's an example of classifications of Lewis bases in hard-soft acid-base theory. So hard-soft acid-base theory, the hard bases are going to be small, and not very polarizable, where soft bases tend to be much larger and polarizable. So in terms of just halogens, fluoride is very hard, where iodide is soft, and bromine being somewhere in between. So this is kind of an example of hard-soft acid-base chemistry here. And same with, like we talked about, the oxides and sulfides. So oxygen or oxide is hard, it is smaller, where sulfide is bigger. So sulfide being soft and oxide being hard. We can do the same thing for acids. So kind of utilizing those same principles. If something is, all right, so we would expect, so in terms of, that was hard soft acid base theory. We can use this for linkage isomers as well. So if you have a thiocyanate, that's gonna, you're gonna preferentially coordinate to a hard metal via the hard nitrogen donor atom. So that's how you can predict that linkage isomer, where isothiocyanate would preferentially coordinate to a soft metal with the soft sulfur donor atom. That would be the scenario. You can actually influence this a little bit with solvents, just like maybe you're familiar with organic for organic chemistry. But low dielectric constant solvents, which generally low polarity, would favor hard Lewis base coordination. Remember, these low dielectric constants, or dielectric constant in general, that's just the ability of that solvent to insulate charges from each other. And generally equated somewhat with just polarity, though it's not the same as a dipole moment, but there are some similarities. That was all structural isomers and hard soft acid base theory. This next time we're going to talk about stereoisomerism in terms of coordination compounds.